Okay, our first surface integral, we're supposed to find the surface area of a surface, and the surface area is found by computing the surface integral of the function 1. Now remember, our surface integral formula is to take the surface integral, turn it into a double integral f of g of uv. What this part means, that means we rewrite the integrand in terms of the surface parameters, in terms of the parameterization that we've done, and we multiply by the magnitude of the normal vector. When we deal with the magnitude of the normal vector in these scalar surface integrals, the sign of the normal vector doesn't matter. But when we later deal with vector surface integrals, the sign will matter, and that's why we talked about outward versus inward facing normal vectors. So in our case, we're going to have a double integral of 1, because the function we're integrating is 1, times the normal vector. Sorry, this should have been a du dv, a double integral over here. So the surface integral just turns into a double integral. If you liked double integrals back in chapter 15, you're in luck because they're back here in this section. Surface integrals are just, after this formula, just turn into double integrals. We, for our normal vector, in a previous video, we saw t cosine theta minus t sine theta t as our normal vector. So the magnitude of the normal vector, we used u and v in general, but we're using t and theta as our parameters, so I'll switch over to that. But the magnitude of our normal vector is the square root of t cosine theta squared plus negative t sine theta squared plus t squared, and that's the square root of t squared cosine squared t plus t squared sine squared t plus t squared. Factor out the t squared in each term in there, and we have a cosine squared t plus sine squared t plus 1. So the square root of 2t squared, or the square root of 2 times t, is the magnitude of our normal vector. So the surface integral, or the surface area that we're looking for, is going to be a double integral of the function square root of 2 times t dt d theta. And for our parameterization, we had t going from 0 to 2, because we're going from the xy plane down below up to where the cone reaches a radius of 2. So t represents the radius of the cone, so from 0 up to 2. And then theta, we're going all the way around, so theta will be from 0 to 2 pi. And at this point, we can do this double integral, right? 0 to 2 pi, square root of 2 t squared over 2 from 0 to 2 d theta. That is 4 over 2 is 2, so 2 root 2 minus 0 times an extra 2 pi from the theta. So we have 4 root 2 times pi as our answer. That's our surface area of this part of the cone, and we get there doing a surface integral. A lot of the work was done in the previous example where we had to find the outward, where we had to find the normal vector. And having the normal vector helped a lot here. And it was also nice, the fact that we were integrating 1 made the integral easier to deal with. But this does come down to double integrals, and we have to stop and ask ourselves, you know, should we do this double integral as is? And in this case we did. You could think of this as, in a sense, as being in polar, but we're not converting to polar coordinates anywhere here. We're using the parameter variables, and the parameter variables were t and theta. So we just used the t and theta. We used the endpoints for t and theta that we found in the previous example, and there was no conversion of coordinates necessary, which is why we don't have an extra r dr, d theta, or anything like that.